All right, well, I got 8 o'clock, so let's go ahead and begin. We're going to be taking a look today at applications of the time derivative. This is material that we're going to cover over the course of 2 lectures. Sorry, my Apple Pencil's freaking out on me. Let's see if I can get that fixed. There we go. All right, so we're going to be taking a look at this over the course of 2 lectures. We kind of started this with our conversation about velocity and acceleration on Wednesday. We're going to continue that conversation today and on into Monday. In terms of where we are in the textbook, we're in section 3.7, 3.8. You do have homework 6. I believe that is due Monday. There are only 10 questions, I believe, on this homework set. It's a pretty light homework set, and you'll be able to do most of it after today's lecture. In fact, you could probably already do most of it. The last 3 questions are from section 3.8, which we'll cover on Monday. So a little bit lighter homework load this week than normal. So what do I mean by applications of the time derivative? Well, we've already seen in this course that the derivative with respect to time of position gives velocity. And we've seen that the derivative with respect to time of velocity gives acceleration. However, there are many other quantities in science that have a time derivative relationship. And we're going to explore a few of those today. And we're going to actually venture outside of physics, engineering, math, STEM, basically, to look at some applications in business, some applications in economics, things like that. So getting back to a couple of more of these relationships, if you have momentum from a physics point of view is just mass times velocity. And so the derivative of velocity is acceleration. So the derivative of momentum would be mass times acceleration. But we know from Newton's second law that mass times acceleration is force. So there's another time derivative relationship. A fourth one would be, say, take the derivative of energy. So this is the amount of energy converted per unit time, or the amount of energy transferred per unit time. And we refer to that as power. And kind of a fifth of our basic relationships that you would find in physics and engineering. These are just some of the basic time derivative quantities. But the fifth one that I want to talk about, and that's where our first example is going to be this morning, is when talking about a circuit. If you have the derivative of charge, you get current. In other words, moving charge is current. And if you know anything about the way a circuit works, if you've taken a circuits class or you're going to eventually take a circuits class, we know that your basic circuit has some sort of battery here, some sort of electromotive force. You have something called a capacitor, and you might have a resistor or an inductor. I'll just draw a little coil on this. So this is what we would call an LC circuit. There are different kinds of circuits out there, but the way that charge works in a circuit is the battery produces these electrons that build a charge. So you've got a bunch of pluses on one end and a bunch of negatives on the other end of this little metal plate. And as electrons flow through this, one side becomes more charged than the other. And the side that becomes more charged will push electrons through the circuit all the way around the circuit. So the charge builds up here, and the notation that we use for charge is Q of T. And then it pushes electrons through the circuit, and the moving charge, which we call current, is usually lowercase I of T for current. Sometimes you'll see uppercase I. What ends up happening, though, is as that current flows through the circuit, it changes the polarity. In other words, all the positives on one side will end up on the other side, so that the current then reverses. And this all happens in less than a second, right? Like fractions of a second. So the current goes one way, it changes the charge, it pushes it back the other way. That's how you get an alternating current. That's what it means by alternating current. So if you go on to study electrical circuits, you'll run into this phenomenon. And what I want to start with this first example is just to say that the derivative of charge is current. So this is kind of our new formula for the day. The derivative of charge is current. So let's take a look at an example. Oh, let me talk about units real quick. For charge, the units are coulombs. Coulombs of charge, and for current, the units are amps or amperes. So those are our units. Changing coulombs per time would be amps. All right, so first example up, want to give you a crack at it here. Suppose we have an electrical fence and we're passing a charge through it, and the charge every second is modeled by the function Q. Which is measured in coulombs. Q is this polynomial function here. What I want to know is, what is the current passing through the fence 2 seconds after the fence is turned on? So according to this model, what is the current in the fence 2 seconds later? So you've got several different amperage choices here. Take a look at it, see if you can correctly calculate it. And if you need the Learning Catalytics session ID, it's up there at the top. All right, I'll give you about another 30 seconds or so. This shouldn't take us very long. We're just kind of getting warmed up. All right, looks like everybody has responded. The correct answer is, with 100%, 9 amps. So the current 2 seconds after the fence is turned on will have a current of 9 amps. The way that we find this is we're simply just looking for the current at time 2. Well, we know the current at time 2 is the derivative of the charge at time 2, which the derivative of the charge is 3t squared minus 2t plus 1, evaluated at time 2. And that gives us 12 minus 4 is 8 plus 1 is 9. So we get 9 amps as the answer. A follow-up question to this is, when is the current at its lowest amperage? So a question we might want to ask here is, when is the current at its lowest amperage? Well, lowest amperage would imply that I'm looking for a minimum of current. So in other words, I'm trying to find where the function I of t, the current function, which we have right here, I'm trying to find when this function has a minimum. Now, the calculus way of doing this is to find the derivative of this function and figure out where it's 0. And where it's 0, it could have a max or a min, but we don't know for sure yet in the course if it's a maximum or a minimum. We can just find it and then check it out in a graph, which is what I'm going to do real quick. So if I take the derivative of current, I'll get 6t minus 2. And if I set that equal to 0, I get 6t equals 2, or t is equal to 1/3 of a second. The units here are seconds. And all I can say at this point is this might be the minimum. I don't know for sure. We're going to have ways later in the course of telling for sure whether this is the minimum value, but I think that this might be the minimum. So I'm going to go check it out in Desmos. So we've got the function t cubed minus t squared plus t plus 1. Let me name that so it knows it's a function. Q of t equals that. And then we're also going to look at, so I wasn't sure that many of you were aware that Desmos could do this, so I wanted to show it to you today. I would love to be able to just type q prime of t and have it graph the derivative. Unfortunately, it won't do that unless your original function was written in terms of x. So I have to, if I want to be able to use that, I have to call this original function f of x. It only does derivative operations if you write it as f of x, then I can write f prime of x and it automatically plots the derivative. So you can see that you've got the function for the charge in red, and you've got the current in green. And we said that we thought that t equal to 1/3 was the minimum. You can look here on the function in green, which is the derivative, and click on it, and you can see that the minimum value is at t equal to 1/3, so 0.3 repeating. There are many opportunities in today's lesson for you to plot things in Desmos and then plot the derivative and look at the two relative to each other. But you can only do that in Desmos this way if you call the original function f of x and then say f prime of x. Now, there's nothing to stop me from actually calculating what the derivative is and plotting that. So that's what I'm going to do real quick. So there is our charge, and we calculated that the current was 6t, the 3t squared minus 2t plus 1. So it's still the same graph. It's just if you wanted to have Desmos calculate the derivative for you, the original function must be in f of x form. All right. So that's just a very simple example. A couple of your homework problems are going to be like this, where you're given some sort of model, say of charge, and you're asked to find the derivative at some point and then interpret what that derivative means. We're going to have a lot more to say about the interpreting part here in just a little bit. All right, so let's try another set of examples. The next set of examples that I'm going to get into are some business applications. So business/economics applications. Now, we've worked with some of these applications already this semester, but we're going to work with several more. So suppose that C of X is cost, R of X is revenue, and capital P of X is profit. Additionally, suppose that X is equal to the number of units demanded. Or you could think of it as units produced, depending on the context. And let's let lowercase p equal the price per item produced or demanded. Then there are some basic relationships between these different variables, these different functions. We know that revenue is price per item times number of items sold or produced. So the revenue here would be P of X times X. We also know that profit is revenue minus cost. But what we want to talk about today is the time derivative of these quantities. So if you take the derivative with respect to time, or excuse me, not time derivative, the production derivative. If you take the derivative with respect to X of cost, then this is going to be something called, we'll call it C prime of X, which is called the marginal cost. And what I want to make sure that you understand here is this quantity rate of change doesn't depend on time. All the other derivatives that we've done up until right now have been derivatives based on time. How does a quantity change over time? This is a quantity that's changing as a result of the number of units that are being produced or demanded. So the quantity cost depends on something other than time. That's not to say we couldn't do a problem where the cost of something did depend on time. That's perfectly valid and actually happens in the real world. But more often than not, quantities like cost, revenue, profit depend on production values or demand values. They don't necessarily depend on time. And so the derivative here is something called the marginal cost. If you take the derivative of any of these quantities, the derivative of revenue, R prime of X would be marginal revenue. And the derivative of profit would be equal to the derivative of revenue minus cost, which is R prime minus C prime. So if you take the difference of the marginal revenue and the marginal cost, you get P prime, which is the marginal profit. So these are different terms associated with some business applications that we're going to take a look at. There's one more value that I need you to be aware of, and that is if you divide any of these terms by the production level. So say, for instance, that we had cost and we divided by the number of items produced. So if this is the total cost for producing X items and we divide by those X items, then this, it turns out to be the average cost per item produced. Oftentimes when we talk about averages in math, we'll put a bar over the variable here. So average cost. And I could do this with any of them. Average revenue and average profit. So all of these quantities we want to kind of keep in our back pocket and look at some problems that discuss and or leverage these. All right, so let's take a look at one. I'll give you one to consider, and then we'll talk about it together. So here's the example. Suppose that this is our cost function for producing X items, and our production range is we can only produce 0 to 1,000 items, so we can't produce any more. There are several answer choices, A, B, C, D here, and I want you to tell me which the following best describes the marginal cost when X is 100 and X is 900. So I'm comparing marginal cost of these two quantities when X is 100 and X is 900. So I give you a second to dive into this and think about the result. Now, to answer this question, you really don't have to calculate anything, but we are going to calculate to confirm. So if you want to calculate something here, you can, but this is based off your understanding of how cost structures work, as well as what the numbers are actually going to tell us. On a lot of these application problems, I'm going to encourage you to use Desmos. We're going to use Desmos to do this one here in a little bit. But if you want to do it by hand to get some practice, I certainly would recommend that as well. All right, I'll give you about another 30 seconds on this. All right, everybody has responded. So here are the results. The correct answer here is C. So these are my options. Let's think through it for a second. When you calculate marginal cost for an item, what you're calculating is the rate of change of cost as you produce more items. So what's happening here is the marginal cost at 100 is falling faster. Your rate of change here is faster than your rate of change is at 100 in terms of the production amount or the price amount in terms of how quickly it's dropping. We could calculate this real quick. So we've got the cost amount here. The marginal cost would be the derivative. The derivative would be negative 0.04x plus 50. And we want to calculate it at 100 versus calculating it at 900. And here's where I would encourage you to use Desmos. So if we'll open up Desmos real quick. Go ahead and write in our cost function. Since we've written it in terms of x, we can use the derivative. So c prime of 100, and it'll calculate it, versus c prime of 900. So the rate at which costs are rising at 100 is faster than the rate at which costs are rising at 900. That's why c prime of 100, which was 46, and c prime of 900 is 14. This is why it's important to have factories, because your cost per item is rising faster if you produce a lower amount of items than if you produce a higher amount of items. The more items you eventually produce, the cheaper it is to make those items, which means the slower your cost is increasing, the more items you produce. Does that make sense, the relationship here? It's kind of a hard thing to sort of wrap your head around, but as you produce more items, the cost is going up slower and slower per item. The cost is increasing much quicker for the first couple of items that you produce, but this is the importance of factories. Mass production allows you to have a smaller cost per item. So I do want to talk about average cost real quick. So we've got the marginal costs here. Let's make sure we understand the units. This 46, what are the units for that? Does anybody know?
Cost per item?
Cost per item. And remember that, you know, when you say C prime of 100 equals 46, another way of saying this is the cost for producing the 101st item is approximately $46. Right? Remember, it's the derivative is always a unit change, meaning you go from whatever you're at to the next unit over. So from 100 to 101. The cost associated with producing that's approximately $46. Versus when 900 units have been produced, the cost from going to the 900th to the 901st is approximately only $14. I want to talk about real quick average cost. So what is the average cost at 100? And what is the average cost at 900? And how do they relate to what we just calculated together, the marginal cost? Is there any relationship between these two things? In fact, are they even the same thing? So that's what we want to discuss. I'm going to go back to Desmos for this. So if I wanted to put in average cost, I could call it A of X is just C of X divided by X, right? The average cost is the cost divided by the number of items produced. So I could easily find the average cost at 100 items, the average cost at 900, and it shows what this shows up here is that as you produce more items, the average cost per item goes down. So if these were jeans, let's say we're manufacturing jeans. If we produce 100 jeans, then it costs us on average $49 per pair of jeans to create. If we create 900 jeans, then they're only around $32.11 per gene that we create. So we can do production, the more production we do, the cheaper per item it gets on average to produce. So this one was $49 and $32.11. So $49 here and $32.11 here. These numbers, I just want you to notice, are not the same as the marginal cost. So the derivative has nothing to do with average cost. In fact, you can see that pretty clearly. We know that the derivative of cost is C prime. What is the derivative of the average cost? Well, the average cost is C of X divided by X, and this is a quotient. So to calculate this derivative, we would use quotient rule. So it's C prime of X times X minus C of X times 1 divided by X squared, which would be C prime of X divided by X minus C of X divided by X squared. So this right here is the average marginal cost. And this quantity is kind of like an offset quantity. It's not really something we really need to get into in this class, but it's not the same as C prime. It's kind of tangentially related to C prime, but the derivative of the average cost is not the same as the marginal cost. And you can clearly see that here, two different derivatives. All right. So the final example I want to look at with you this morning is going to ask us to use a lot of Desmos. We're going to do parts of it by hand, but we'll do parts of it in Desmos as well. And that is we're going to look at the spread of a rumor. So the function P of t equal to 1 over 1 plus ae to the minus kt, this function is what's known as the logistic curve. I'm going to graph it for you here in just a second and show you what the values of a and k do. And what I'd love to know is, according to this curve and according to this model, tell me what happens as t goes to infinity. So you've got several different options here for what happens to the spread of the rumor over time. So P of t, the units for P of t is the proportion or percentage of the population that has heard the rumor at time t. So I want you to tell me which of these represents before, don't graph it, right? This is all based off of intuition, looking at the function, understanding what's going on here. Which of these is the correct limit at infinity for this model? So thinking of taking the limit at infinity for this function, given the context, which of those is correct? I'll give you a chance to think about it and we'll talk about it ourselves. All right, I'll give you about another 30 seconds or so. All right. So here are the results. The correct answer is D. The limit as t goes to infinity of this function is 1. Can someone give me a reason that doesn't involve a calculation? What's the reason that this is 1?
Since the Euler's number, the exponent is negative, it'd be approaching 0 at infinity. And then you just add 1 plus 0, and there'd be 1/1.
Okay, so that's a calculation. You're calculating the limit when you say that, and you are correct. The calculation of this limit is 1. We'll show that in a second. What's a contextual reason for why the limit is 1? Has nothing to do with the calculation, just the context of what this function represents. So this function represents a proportion of the population that has heard the rumor. Why does it make sense that the limit at infinity is 1?
Because eventually everyone hears a rumor.
Right, and what is 1 as a percentage?
Everybody.
Yeah, 1 is 100%. So 100% of people, or the proportion 1, 100% of the people will have heard the rumor as time goes on. So let's calculate the derivative of this thing together, look at the limit together, and then we're going to do the rest of this problem in Desmos. So if I take the limit as t goes to infinity of p of t, as was stated, the calculation here is kind of easy because you have this decaying exponential in the bottom. So this term right here, the limit of this term, it goes to 0 over time because it's decaying. And so you're left with 1/1 plus a times 0, which is 1/1, which is 1. So eventually, 100% of the population will hear the rumor according to this model. Now, the curve that we're looking at here is called the logistic curve. Let me show it to you in Desmos. So our function here is p of t equal 1/1 plus a times e to the minus kt. And I'll put in some sliders for a and k so that we can see those values. So here is this function. You can see that it starts at, when k is 1 and a is 1, it starts at 0.5 and it goes up over time. You can see that as I change a, right, we get a either steeper or less steep approach to 1. And as I change k, that really either steepens or flattens out the curve. So it's like how quickly, k controls how quickly everyone will hear the rumor, and a controls the starting number of people that hear the rumor. Notice if I just switch k, it doesn't change the starting amount, but if I switch a, it changes the starting amount of people that hear the rumor. And there are only certain values of a that work, right? We can't go below, we can't make a negative a because you can't have negative people that have initially hear the rumor. And then the bigger a gets, the less people initially hear the rumor, the longer amount of time it takes before you get full saturation. So this kind of curve is actually really important mathematically, and it models far more than just the spread of rumors. It can model the adoption of new technology. So how quickly does everyone get an iPhone, for example? It can model populations. So you've got some sort of population here that grows exponentially for a while, but then due to lack of resources or something like that, the population doesn't grow as quickly, and there's a cap on the maximum size that the population could be. So this is called a logistic curve or logistic growth. So I said graph this thing and its derivative for 10, for a equal to 10 and k equal to 0.5. So let me change that out real quick. So we're going to make a equal to 10 and k equal to 0.5. So here's our logistic curve. We change the window here slightly. This will keep everything nice and in frame. And what I want to do is I want to look at and calculate the derivative of this thing. So let's do that by hand just to get a little bit of practice at this, and then we'll graph it here together. So in terms of doing it by hand, if I know that P of t is going to be, let's see, so A is 10, so this is 1 over 1 plus 10 e to the minus 0.5t. I want to find the derivative of this function. So in order to do that, I could use quotient rule because this is clearly a quotient, but let me suggest that the better way to do it is to think of this function, 1 plus 10 e to the minus 0.5t raised to the negative 1. And so if I take the derivative of that, the derivative of this is you've got something raised to the negative 1. So it's negative 1 times that thing raised to the negative 2, according to power rule. But then I have to multiply by the derivative of the inner function because of chain rule. So this would be negative 1 over this quantity squared. And then the derivative of the inside function here, the derivative of 1 is 0. The derivative of the exponential is 10 e to the negative 0.5t. You get the exponential back, but you have to multiply by negative 0.5 because of chain rule. So negative half of 10 would be negative 5. So you would get negative 5 e to the minus 0.5t as the derivative there. And if you make everything look nice, this is the function that you will get. Now, before I plot this function in Desmos, which I'll do here in just a second, I want you to tell me, so let me bring Desmos back here. I want you to tell me where on this curve do you think the rumor is spreading the fastest? Because the derivative we just calculated is going to be the rate of change of the spread of the rumor. So where on this curve does it look like the rumor is spreading fastest? And does that make sense contextually?
5. About halfway through 5.
You think right here?
Yeah.
Okay, does anybody have another guess?
At the beginning, around
Yeah,
like 1 or 2.
Do you think at 1 or 2? Okay. Well, the way that we can figure this out is by graphing the derivative. So the derivative function here, I'll call it S of t for spread. 5 times e to the negative 0.5t divided by 1 plus 10 e to the minus 0.5t quantity squared. All right, so where does it look like this is the derivative that we just calculated together? Where does it look like the derivative is at its highest point? Looks like right there. So that corresponding value here, so what is that, 4.65? So let me kind of figure that out again. So it's 4.605. So 4.605 and then P of 4.605. Sorry, little p. That is the point on the curve at which it's rising the fastest. The significance of that number is 0.5, right? Do you see that that's at 0.5? So explain to me what we just found. When is a rumor spreading at its fastest?
When half the population has heard the rumor.
When half the population has heard the rumor. And it's the same for the spread of technology. That's what the logistic curve will always predict, is that the rate of change of adoption of technology, the faster people are adopting technology, is when half the population has something. Or if you're talking about population growth, if say a group of rabbits is growing logistically, it's growing at its fastest when it's reached half of its potential maximum, which is half of the carrying capacity. So this is a relationship that you will always see between the logistic curve and its derivative. And it's kind of a fascinating relationship that we actually take advantage of in other courses, like a differential equations course, for example. What I want to encourage you to do with these examples is to embrace using Desmos to do application problems. If I'm giving you an application problem on a test or on the homework or whatever, I'm not really testing your ability to calculate derivatives by hand at that point. I want you to use Desmos to help you graph these things, to give some arguments, but you have to write down your work, obviously, when you're turning something in. You have to show me what it is you did, but I want you to embrace using Desmos to help you do this. You don't have to do every single little step by hand. In fact, if I wanted to, I could have gone back and written this as a function of x so that I could use Desmos to take the derivative. So there's that. And rather than calculating the derivative by hand, I could have just said, calculate the derivative, p prime of x. What is p prime at 2? So that's how quickly the rumor is spreading at what were my units for time here? Hours. So that's how fast the rumor is spreading 2 hours later. I could have also looked at when half the population has seen the rumor. So y equal to 0.5, and I could have calculated that maximum there. There's lots of ways that I could have used Desmos to analyze this problem, and I want you to embrace that on a lot of these application problems. It'll make them go faster, and it'll help you get a more clear picture of what's happening in the problem. All right, that's all I had planned for today. I wanted to look at a couple of examples to tell you kind of the techniques and things to look out for as you're working on the homework this weekend. Y'all have a great weekend, and I'll see you back on Monday.
When will this Zoom meeting be posted? Or
the video, usually, because I've got class at 8, 9, and 10, usually once my 10:20 class, once that class is over, which is 11:10, then I post them during lunch. So usually they're up by 11:30.
Okay, thank you.
Yep.
And where can I find them? On YouTube or?
I make an announcement. Each time
Okay.
I've done this, I make an announcement on Canvas, and I just embed the video in that announcement.
Okay, thank you.
Yeah, no problem. Have a good weekend, everybody.
Have a good weekend, sir.
Yeah, you too.